Welcome back, everybody. So we are going to look at some examples here of using left or right endpoints as well as midpoints. So let's go ahead and start. So we're going to estimate the area under the function y equals x cubed on the interval 0 to 1 using 5 subintervals. So we know what n is, and we know what our interval is. So these have to be given, otherwise we're not going to know exactly how to correspondingly find the area. And for all of these examples, I'm going to highly recommend just drawing a quick sketch of what that graph is going to look like. So we know x cubed is going to look like this. And then what we can do is zoom in a little bit. And we want 5 subintervals. So let's suppose, 1 is here, 0 is here. So we're going to just split our area into 5 subintervals of equal length. So they're all going to be the same length. So we'll note first, delta x is going to be the length of our interval divided by our number of subintervals. So we're going to go in increments of 1/5, obviously. So we've got 1/5, 2/5, 3/5, and 4/5. And we're going to use left endpoints for this example. So I did change it from right endpoints. We could have done right endpoints as well, but good to maybe see a left endpoint example. So then that means that we're going to be taking the left endpoints as our rectangle heights. So I'm going to take all these points and I'm going to make them the left endpoints, which means from 0 to 1/5, there's nothing because the height is 0. And then from 1/5 to 2/5, we'll take the height at 1/5. 2/5 to 3/5, we'll take the height at 2/5. 3/5 to 4/5, we'll take the height at 3/5. And then finally, from 1. So if we were doing right endpoints, we would start on the opposite side. So we'd start with this endpoint and then work our way backwards. So if we did right endpoints, our area would look like that. So obviously an overestimate if we did right endpoints. Okay, but we'll do left endpoints. All right, so then our goal is to, figure out all the areas of these rectangles. Okay, so then we can see that the area of the left is going to be 1/5 times f of 1/5 plus 1/5 f of 2/5 plus 1/5 f of 3/5 plus 1/5 f of 4/5. All right, so just taking the area of each one of those separate rectangles, again with delta x being 1/5. We don't need to include f of 0 because there's no height. There's 0 height there, so we're only going to have 4 terms for our summation. So we can factor out the 1/5, and then let's cube all of these. So we'll have 1 over 125 plus 8 over 125 plus 27 over 125 plus 4 cubed is 64 over 125. So we're going to end up with, it looks like 64 and 27 is 80, 91, and 9 is 100. Let's double check that, 35, 36, yeah. So it's going to be 100 over 5 times 125. We can cancel the 5 and the 100, so we can simplify this a bit. That'll be 20. And then we can divide another 5 out. And it looks like we're going to get 4 over 25. All right, so 4 over 25 is our estimate area. We can see here clearly it's going to be an underestimate. And again, you can do the right endpoints and we'll just add on. So if we did right endpoints, that would just result in us adding on one more additional term, which would be at f of 1. So note this would be for a sub r. So that would just be 4 over 25 plus 1 over 125. And so we could multiply that by 5, and I think we get 21 over 125. So again, the right endpoints is very similar. It's just your heights are going to be slightly different. Okay. So let's look at the second example. Now we're going to use right endpoints with the curve 1 over x. So again, I would highly recommend drawing a quick graph. So we're going to go from 1 to 6. Oops. And now we know that 1 over x is going to be this decreasing function. And we can kind of maybe cut it off here. So it's exactly between those two values, and so we don't need the remaining portion, but we do need to split it into 4 subintervals. So let's go ahead and do the subintervals. 1, 2, 3, good. And we are using right endpoints. So again, we'll start here. So our first location is there. So our right endpoints is going to be a slightly smaller rectangle each time from left to right. And actually, we don't need to highlight this portion up here. We're not including that. Oops. Okay, so that's going to be our right endpoint approximation. So we know our interval, we know our number of subintervals, so we'll note delta x is 6 minus 1 over 4, which is 5 over 4, or 1.25. So what I'm going to do then is I'm going to rewrite this slightly, maybe as, instead of 1, I'm just going to write it as 4 over 4. And then just add 5/4. So we'll have 9/4, 14/4, which is 7/2. And then plus 5/4 is 19/4. And then we end up with 24/4, which is just 6. So those are our subinterval lengths. So just note they're not always going to be perfect integer values or anything like that. They can get a little messy, but this should be pretty straightforward to calculate. So we'll have the right sum is going to be delta x times all of our function values. So it's going to be f of 9/4, f of 14/4, plus f of 19/4, plus f of 6. So those are our right endpoints. So what we'll end up with is 5/4. Now our function is just 1 over x, so we just need to reciprocate the x values, right? So 9/4 becomes 4/9. 14/4 becomes 4 over 14, which is the same as 2 over 7. And then 4 over 19, and then 1 over 6. Okay. And then this one is obviously one that probably not going to require you to do it without a calculator, because obviously the common denominator here is going to be quite messy. So we can go ahead and put this into our calculator and see what we get. So we've got 5/4 times 4/9 plus 2/7 plus 4/19 plus 1/6. So we should get 1.384. 189,641 is what I've got in my calculator. And what we'll note for the AP standard, we need it accurate to at least 3 decimal places. So you could include all these numbers, but you have to have at least 3. So 1.384 would be the truncated value at 3 decimal places. So 1.384 is a perfectly fine answer. More decimals than that is also fine. All right, and then our last one that we're going to look at here before we move on to formalizing our summations is midpoints. So for midpoints, what we're going to do is we're going to take our curve here, which is 2x squared. So we're going to have a quadratic, and we're going to consider it from 0 to 2. So let's go ahead and kind of fill in the values here. So we're given actually delta x to begin with, which is 1/2. So we're going to have 4 subintervals. So we'll have 1/2, 1, and 3/2 going up to 2. And then what we're going to do is, for the height of each rectangle, the height of each rectangle is going to be at the, midpoint of each subinterval. So again, you're just going to approximate the midpoint, find it there. And then we're going to construct rectangles that are that height. So this is a much more accurate method. Actually move that a little bit. More like here. Because it's going to be a little bit overestimating as well as a little bit underestimating. But this is going to be a much more accurate method than doing it simply with left and right endpoints typically. And we'll just note that those midpoints are going to be the fourth terms, the over 4 terms between those. So 1/4, 3/4, 5/4, 7/4, because those are going to be the heights of our functions now, right? So the height here is f of 7/4, not one of the right or left endpoints. And then we'll do the exact same area calculation. Let's go ahead and do that. So we've got a sub m is going to equal delta x is 1/2, and then we'll have f of 1/4 plus f of 3/4 plus f of 5/4 plus f of 7/4. So that's going to be 1/2. 2x squared is going to be 2/16, which is 1/8, plus 2 times 9/16. It's going to be 9/8 plus 25/8 plus 49/8. All right, so we're going to get, looks like 74, 83, 84/16, which is 21/4, I believe. So it should be 21/4. And that's going to be our approximation using midpoints. So again, midpoints, you just use the midpoint of the subinterval instead of the right or left endpoints. Okay, so then what we want to do though now is we want to make this more accurate. So obviously these are approximations that we just did previously. So you might ask yourself, well, how do I make this more accurate? And the obvious answer is going to be make the subintervals smaller, right? Because the smaller the subintervals and the more rectangles you have, the smaller those over and underestimated areas are going to be. So let's suppose that we partitioned our curve into n subintervals. So we're going to assume that we've got each subinterval then is going to be 1 minus 0 over n in length, which is just 1 over n. So we've got 0, 1 over n is the first subinterval, 2 over n, 3 over n, 4 over n, and so on until we get to n over n, which is just 1. So we're going to have all of these, and you'll notice 1, 2, 3, 4, 5, 6, all the way up to n is a nice summation. So what we're going to get then is that we can write the area A, in this case it's with right endpoints, and so we'll use the we'll use 1 over n as our first, as our first height. It's kind of hard to see there, but so we'll have 1 over n, f of 1 over n plus 1 over n, f of 2 over n, all the way up to 1 over n times f of 1, which is just n over n. And then we can factor it out, the 1 over n. Then we'll have f of 1 over n plus f of 2 over n plus f of n over n, which is again just 1. But we'll notice that these are all just x squareds. So this is 1 over n, sum I equals 1 to n of f of I over n is one way we could write it. We could also use the explicit x squared rule. So if we wanted to do it that way, we could do 1 over n, sum I equals 1 to n, and then we could just do I over n squared, where each I over n squared term is each value of the function. But we've seen this before, right? We've evaluated this before, right? It just doesn't look like it. So if we take this right expression, let's note that we can multiply the 1 over n inside if we wanted to. So note we could have the sum I equals 1 to n. I'm going to rewrite this as I squared over n squared. So I'm just going to individually square each term. And then I'm going to move that 1 over n inside. So what we end up with is I equals 1 to n of I squared times 1 over n cubed. And if we think about that sum, I squared times 1 over n cubed, and we go all the way back to the beginning, there it is. So that limit of the sum that we looked at there was actually describing the area underneath the x squared curve with n subintervals. Now we know that that's equal to, when we take the limit as n goes to infinity, so from page 1, and note that's equal to a, the limit as n goes to infinity of a is equal to 1/3, which means the exact area under f of x equals x squared on the interval 0, 1 is 1/3. 1/3 is the exact area underneath that curve, which is pretty amazing that we can find that just using this simple rectangle process and then applying a little limit at the end to it. And so what we call this limit that we're taking here is again called the limit of a Riemann sum. So on the next page here, we've got this generalization. So in general, for any function, we can subdivide it into however many subintervals. They call them strips there, S1, S2, S3, but they're really just subintervals where we're calculating area. Note, for our focus, we were doing rectangles everywhere. But suppose that they had some fancier method of finding each one of those strips possibly, so it looks like it's, perfectly uniform. So the area of the region in the plane, right, so underneath that curve, is going to be represented by this infinite limit of this combination of expressions. And we'll just note that this was our f of x's, right? F of x sub i's, you could call them, right? So this was our function value, which was the height of each rectangle. And then this 1 over n is delta x, which is the width, right? So this is the sum of the areas, right? Obviously, from our construction, we can see it's the sum of those areas. But this is the key expression, so f of x sub I delta x. So we're taking the sum of each one of those f of x sub I delta x's, which they kind of write in the long form here, and then they compact it here. So this is going to be the area under the curve of any function that we subdivide in that way. So we want to write the expression of the area underneath the curve of y equals x cubed on the interval 0 to 1, and then evaluate. So let's go ahead and look at this example. It's going to be very similar to what we just worked on. So again, we can draw a quick little graph here. We've got our x cubed term from 0 to 1. And again, we're going to subdivide it into, n subintervals. So there's going to be a whole bunch of rectangles all over the place here. So we'll note that delta x is equal to 1 minus 0 over n, which is just 1 over n. And then our area is going to be each one of those rectangles. So 1 over n times f of 1 over n plus f of 2 over n, all the way up to f of n over n, which is just 1. But each one of those is just cubed, right? So that's just going to be 1 over n, and then we'll have 1 over n cubed, 2 over n cubed, up to up to 1 cubed. But then we can rewrite that simply as 1 over n sum I equals 1 to n of I over n cubed, which then we can bring the 1 over n inside to make it look like f of x delta x. And now we can take the limit as n goes to infinity of that. So we'll take the limit as n goes to infinity, which is going to represent our area A of the sum I equals 1 to n. I'm going to combine the n cubes there. So we'll have I cubed, and then this is going to be 1 over n to the 4th. But the 1 over n to the 4th I could just factor out, so we're just going to rewrite that with the I cubed summation. So we'll have the limit as n goes to infinity of one over n to the 4th times the sum of I cubed was n squared times n plus 1 squared all over 4. And so if we note the leading term here in the numerator is going to be n to the 4th. So we're going to have an n to the 4th, which is just 1 n to the 4th. So this summation is going to equal 1/4. So the area underneath the x cubed curve from 0 to 1 is 1/4. And again, I'll just note where we're headed, which is we're going to simplify this into simply the integral from 0 to 1 of x cubed dx. Take the antiderivative. and then evaluate its difference at each point. So all that work we just did is going to become this eventually. So we're going to be shorthanding this work quite a bit, and we won't have to do all of the summation work. But the key idea is that the limit is the foundation of the area. We need to take this infinite limit in order to get this exact area. So just like derivatives being the slope of the secant line, a representation of the slope of the secant line as we shrink the distance between our 2 points, then as we add more and more and more and more areas and more rectangles, we shrink the error in our area calculation until the error is 0. And so the area will be the exact true area. Okay, so that's going to kind of conclude the notes here. We've got some additional exercises, which I'll fill in some solutions for. So you can check the notes online for those. So if you do have questions, definitely email me or come by the office hours. Otherwise, until I